Hello everyone. Now in this section we're going to learn how to synthesize a carboxylic acid. And our starting material for the synthesis of the carboxylic acid, we use diethyl malonate or the malonic ester. Malonic ester is the common name. It is a diethyl malonate and we call this process as malonic ester synthesis because the starting material is malonic ester. But what we are synthesizing is a carboxylic acid. And why do you call it malonic ester synthesis? We are not going to synthesize malonic ester, but our starting material is malonic ester. So that is why this process is called malonic ester synthesis. Okay, so this is the malonic ester. So the ester functional group is carbonyl group and you have oxygen and an alkyl group. Now this is diethyl malonate. You can see here there are two ester groups here, not just only one ester. Okay, so it's a diethyl because this is ethyl, this is ethyl, it's diethyl malonate, malonic ester. Now let's see how we are going to synthesize an acid with the malonic ester. For example, first thing is you need the malonic ester and then you're going to react it with a base. So the base is again going to be ethoxide. You see here this is the ethyl group. Remember we learned in a previous section that if you have an ester, it's always good to have the same alkoxide similar to the alkyl group in the ester. So this is C2H5, this is also C2H5, ethoxide ion, going to act as our base to grab the acidic proton. So our acidic protons are going to be these two hydrogens. Remember? So first thing is you deprotonate one of the hydrogens and form the enolate ion. Or now since you guys know that there is an enolate ion going to happen here, you can consider once the hydrogen is lost, this is a carbon ion. Okay, and then you're going to react that with alkyl bromide. Now this is going to act as a nucleophile and going to attack the alkyl group and it's going to leave bromide. So the alkyl, the R group will be attached to this carbon. And then the third step, what we're going to do is we're going to add an acidic water and you heat it. Now under these conditions, acidic condition, acid water, and when you heat it up, you're going to hydrolyze the ester. So this is the ester. Ester will hydrolyze to give you a carboxylic acid, two carboxylic acids. And then in the process of heating, we can also remove a carbon dioxide. So a lot of things are happening in this reaction, but we'll look at it one at a time. Okay, you'll get it. So this is the product at the end after you add the nucleophile, then you react it with the alkyl halide and then you hydrolyze the ester with acid and you heat it up, carbon dioxide lost. What you're gonna get at the end is this molecule. You start with the malonic ester. What do you have right now? Now you have an acid. COOH is an acid. Now this part, so this CH2 and carbonyl group, this will become an acid. This part come from the malonic ester, and this alkyl group will come from the alkyl halide. So the bottom line is the ester, not the ester, sorry. The acid that you're going to get is going to be the alkyl halide that you're going to use plus 2 carbon long acid. That's the bottom line. When you start with the malonic ester, the acid that you're going to get is the alkyl group plus the 2 carbons because these are the 2 carbons coming from the diethyl malonate, making it an ester. So malonic ester synthesis forms a carboxylic acid with 2 more carbons than the alkyl halide used in the synthesis. Now let's see how we're going to do the steps and get to the final product. So this is the malonic ester. You add ethoxide, which is a base that will help you to remove the alpha hydrogen from the alpha carbon. So these are going to be your alpha hydrogens. We have seen it before. So the two hydrogens, these two hydrogens, when you add ethoxide CH3, CH2O minus, gonna grab one of these hydrogens and form carbon ion, and it's going to be resonance stabilized. We know all that. Okay, now once you form the carbon ion, now you have an alkyl halide group. So you can see how the arrows goes. Carbon ion, always electron flow takes place from where you have more electron density to the less electron denser atom. Okay, so carbon ion goes and attack the alkyl group and then leaves bromide. Okay, so the alkyl group will end up attaching to that carbon, that is this molecule right there. Okay, now we have an alpha substituted malonic ester, easy, right? That step is easy. Then what's going to happen next? Next is you're going to be adding HCl and water, and you heat. And under these conditions, you see here is an ester group, here is an ester group. This ester will hydrolyze. Ester hydrolysis will give you acid. Okay, so it's going to give you this acid. So you see here, so this bond going to break carbonyl group. So you're going to be adding OH to either side to make them an acid, and from the other side ethoxide will become ethanol. So two ethanol groups from here, C2H5OH, C2H5OH, that's going to be 2 ethanol. Okay, so basically what's happening is during the hydrolysis, what's going to happen, so you're going to break this bond. Hydrolysis means you're adding a water molecule, H2O. It is OH and hydrogen. So H goes to this side, OH goes to this side. So breaks here, H goes to this side, OH goes to this side. So it's become COOH, COOH. So in the next chapter, I will explain you the mechanism, how it happens. But for now, know that when the ester is hydrolyzed, it forms acid. Okay, since there are two esters, you have two acids, and then you also have two alcohol groups. Okay, now do you understand here? Do you see a pattern that we learned earlier section about the decarboxylation? Remember, we talk about that the decarboxylation take place when you have a carbonyl group in the third position to the carboxylic acid. This is 1, 2, 3. If you consider this carbon as carbon number 1, so in the third position you have a carbonyl group. So that will make the carbon dioxide to lose during the process of heating. Okay, so if one carboxylic carbon dioxide molecule lost, what you're going to get is this product at the end. Let's see if I can show you the mechanism in the next one. No, but I'll just remind you how the decarboxylation happens. So we can go ahead and number those ones. So I'm going to redraw that molecule, this molecule over here, OH, CO, CH, you have an alkyl group there, and then you have a carbonyl group, oxygen, hydrogen. It's the same molecule. I redrew it so I can show you. Why are you not erasing? Okay, now good. Okay, so if you number these ones, I would go ahead and write this one as number 1, 2, 3, 4, 5. So this is your number 1, 2, 3, 4, 5. Okay, I rearrange the molecule. I kind of bend it and make it to a 6-membered ring, so it's at a nice transition state. So what's going to happen next? You will see that this bond going to go and make a bond with the hydrogen. Then 4 and 5 bond breaks to form a bond between 3 and 4, and then the 2 and 3 bond breaks to form a bond with 1 and 2. So what we're going to get is, from the left side we have a OH, and then we have another OH right there, and then you have a double bond, and then you have a R group. And from the other side, so this is number 1, this is number 2, and from the other side, number 4 oxygen, this is number 4 oxygen, forms a double bond with the carbon, and this is carbon number 3, and then 2 and 3, remember the 2 and 3 bond break, so this is carbon 3, and then the 3 also has an oxygen on it, like that. So that's a carbon dioxide molecule. Okay, now the left molecule, which you have 2 alcohol groups, now that's the enol form. It would rearrange to give you the keto form. So if I draw it over here, OH, this can happen in the acidic medium or the basic medium. Okay, so basically this can, one of these oxygen can form a double bond, and this can go and grab hydrogen, maybe from ethanol or water, can grab a hydrogen, H plus, if this is happening in the acidic medium. And then you have this molecule OH, OH plus, R group, this is CH2, and then R. So the hydrogen will be here. Okay, and then what's going to happen? Another water molecule comes and take this hydrogen, and this will give you this OH, CO, CH2R. This molecule right here is same as this one here. You see, that's what happened. Alkyl group and then the carboxylic acid. So in the malonic ester, what happened? You start with the malonic ester and you use a certain alkyl group. You use R. So at the end you are getting an acid with 2 more carbons than the alkyl halide. That is the importance of the malonic ester synthesis. Starting with the malonic ester, you are getting an acid which has 2 more carbons than the alkyl group in the alkyl halide. Okay, I hope you got it. Okay, now synthesizing a carboxylic acid with 2 substituents. In the previous one, we added only 1 alkyl group. Now remember, in the malonic ester, there are 2 hydrogens. If you lose 1 hydrogen and you attach it to alkyl group, you have 1 alkyl group attached at the end. But if you want to add 2 alkyl groups, you can do that too, because there are 2 acidic hydrogens. Let's see how to do that. Now this is your malonic ester. You add nucleophile, which is, or the base, which is going to be same as the alkyl group of the malonic ester, which is ethoxide, and with that it's going to grab the proton from here and you form your carbon ion, which is conjugated and resonance stabilized with the carbonyl group, and this carbon ion react with the first alkyl group, attach the alkyl group onto the alpha carbon. Now after you add that alkyl group, if you want to add another alkyl group, you add 1 more equivalent of ethoxide. Here's another acidic hydrogen, you form the carbon ion, and next time you react with a different alkyl halide. This is R, this is R prime. So carbon ion react with the alkyl group, loses bromide. Now you have two alkyl groups on the alpha carbon to the ester. Okay, what's the next step? You add hydrochloric acid and water to do what? To hydrolyze the ester to give you two acid groups. And when you heat it, from the mechanism that we know right now, the carbon dioxide molecule loses. So you lose carbon dioxide and you will get from this side, you get the acid. R, there are two alkyl groups, R and R prime on this carbon, and then carboxylic acid. Okay, so this is how you're going to be synthesizing a carboxylic acid with two substituents. And let's say if the R group needs to be the same one, so instead of alkyl bromide, R bromide, R prime bromide, you can react both times with the same alkyl halide. So then these two substituents are going to be the same. Okay, it's not that hard. Okay, now let's say you want to plan a synthesis of a carboxylic acid. Okay, you want to plan this one. So you are given this carboxylic acid and you are asked, hello, can you go ahead and synthesize this carboxylic acid for me? And then we know this part we can get from the malonic ester, because we know a malonic ester at the very end, when you hydrolyze and you heat it up, it will become acid and decarboxylation, and at the end you're going to be getting this part, and the alkyl group can come from the alkyl halide. And if you are asked to synthesize this acid, then we know this part, CHCOOH, carboxylic acid part, can come from the malonic ester. This alkyl and these two types of alkyl groups can come from two different alkyl halides. So you know how to synthesize the carboxylic acid from the malonic ester. Okay. That's about the malonic ester synthesis. So what do we get from the malonic ester synthesis? We get a carboxylic acid with 2 carbons more than the alkyl halide that we use. Now this is a different ester synthesis. Different synthesis meaning for this synthesis, the starting material is acetoacetic ester. Acetoacetic ester. So the both of these syntheses were named based on the starting material, not the end product. Okay, so this is the acetoacetic ester synthesis, and now this one is the acetoacetic ester. What's the difference of this from the malonic ester? Remember the malonic ester, here also you had a ethoxy group, meaning another ester. But in this one, only one side is ester, but the other side is a methyl group, aceto group. Okay, so this one is ethyl. This is how the ester is being named. We'll learn it in the next chapter. Ethyl, you have an ethyl group, 1, 2, 3, 3-oxobutanoate. Why butanoate? 1, 2, 3, 4, butanoate. Don't worry about the naming yet. We'll learn the naming in the next chapter. Okay, but this is the common name for this one is acetoacetic ester. Okay, now what are we going to get in the acetoacetic ester? At the very end, you are making a ketone with an additional alkyl group coming from the alkyl halide. The process is pretty much similar to the malonic ester synthesis. Remember the malonic ester synthesis also, you had a ethoxide ion, CH3CH2O minus. Excuse me. What does the ethoxide do? Now you know what it's going to do. It's going to deprotonate your alpha hydrogen. Same like the malonic ester, then that's going to react with alkyl halide. So the alkyl group will add on to this carbon. Okay, and the same steps. And you add HCl and water. When you add hydrochloric acid and water, the ester will hydrolyze to carboxylic acid. And then we heat it up to decarboxylate. Once this decarboxylate, you're going to lose this whole part. And then what we left is the alkyl group attached here. Okay, so the product would be alkyl group and this part. So in the acetoacetic ester, you're gonna retain this part, which is this green part over here. CH3, CO, CH2. Whatever the alkyl group will end up on here. And this part, the other part, this part will be lost as carbon dioxide at the very end. Okay, easy. I hope. Yes. Okay. So, acetoacetic ester synthesis forms a methyl ketone. Because our starting material, we have a methyl ketone part. This part has to be there. A methyl ketone with 3 more carbons than the alkyl halide used in the synthesis. So now do you see in the acetoacetic synthesis, 1, 2, 3. So these 3 carbons going to retain 1, 2, 3. So at the end you are getting a ketone, a methyl ketone, 3 carbons more than the alkyl halide you start with. If the alkyl halide is methyl, this would be CH3. Ethyl, C2H5. Propyl, C3H9, like that. Okay? So these are all important in synthesis. Okay, let's go to the next one. The steps in the acetoacetic ester synthesis. Now you start with acetoacetic ester. This is the aceto part, acetoacetic ester. You add a ethoxide because this is the ethyl group. We need to match it. Ethoxide. Take the hydrogen, form the carbon ion, remove a proton from the alpha carbon. And then the first step is you alkylate the alpha carbon. Carbon goes and attack the alkyl group, lose bromide, and then alkyl group will be added on to the alpha carbon. Same steps. And then you do the hydrolysis. When you do the hydrolysis, this part will not hydrolyze because it's a carbon-carbon, but we only have ester in this part. So when an ester is hydrolyzed, you break this bond, meaning you can consider it as adding a water molecule across the carbonyl group and oxygen. OH goes to this side. OH didn't go to the side I want. Okay, I'll redraw it. OH. Okay, OH goes to this side and hydrogen goes to this side. From this side, you are making ethanol. And for the other side, you have the carboxylic acid. Now, when you heat up, you know what's going to happen. You're going to lose the carbon dioxide. So, you're going to basically lose this carbon dioxide. And you also know the process and the mechanism, how it happens. Remember, I'll redraw it to remind you. CH3, CO, CH, you have alkyl group. And then I'm going to put my carbonyl on the side. Oxygen here, hydrogen here. So this is how the decarboxylation takes place. So this is going to go and grab the hydrogen. This oxygen-hydrogen bond breaks, forms a carbon dioxide. So the molecule you're going to make CH3, OH, R plus carbon dioxide. And this is the enol form. The keto form would be formation of the methyl ketone. CH3, CO, CH2 alkyl group. So from the acetoacetic ester synthesis, we have a ketone made 3 more carbons than the alkyl group. Okay? Okay. Planning the synthesis of a methyl ketone. Now let's say you are asked to make this methyl ketone. If it is a methyl ketone, then you know, hey, I can get this part from the acetoacetic ester because I know at the end, even though I start with the acetoacetic ester, this is what I'm ended up with. And this alkyl group can come from the alkyl halide. Okay? Okay. So designing a synthesis that makes a new carbon-carbon bond. Locate the new carbon-carbon bond that must be formed. Now you are given So you are asked to make this molecule from this one. Okay, now this is the given molecule, and then you have a carbonyl group over here, and then we can consider this is the new bond that has been formed. So if you break from here, what's going to happen? We can number them and see what is happening. Number 1, 2, 3, 4, 5, 6, 7, 8. You are breaking 1 and 8. So this is going to be your 1, 2, 3, 4, 5, 6, 7, 8. So you are going to make a connection between 1 and 8. So basically there is a hydrogen right there. So if you add a base, what's going to happen? You can form a carb anion there. Carb anion, and then this can go and react with this carbonyl group, form the carbon-oxygen bond, opens up, reform it, and leave OH, so you can get the product. Okay, and then designing a synthesis that makes a new carbon-carbon bond. Decide which end will be the nucleophile and which end will be the electrophile. So we can consider nucleophile to be here, because you know there is a carbonyl group. This is alpha carbon carrying alpha hydrogens which are acidic. So if a base will remove this proton, it will become a nucleophile, and this side could be the electrophile. Okay, or you can do it the other way. So this become the electrophile and this become the nucleophile. I like this one over here. So how are we going to make it together? So if you start with this molecule over here, so here we are given this molecule. Okay, so the starting material, first thing you can make a thionyl, add a thionyl chloride. So when you add thionyl chloride, so this would become COCl, chlorine. Okay, acyl group. Acyl groups are good at making esters compared to OH. So what you're going to do is, so this alcohol first convert to chloride, and then when you add the methanol, acyl group and the methanol will make a methyl ester. Now you can add a methoxide. This will become negatively charged and attack the carbonyl carbon, and then leave this methoxy group to give you the product. Okay, the same thing that we talked about earlier, the same process, but instead of keeping it as alcohol, you first convert it to acyl group by adding a chlorine, and then making an ester, because ester methoxy group is easy to lose. Okay, so that's how the synthesis is being carried out to form the desired product. Okay, so another one. Designing a synthesis that makes new carbon-carbon bonds. Locate the new carbon-carbon bonds that must be formed. So you are asked to make this molecule starting from this one. Now this one is malonic ester, right? So you want to make this product from that. So we can consider here's a acidic hydrogen, 2 hydrogens, and you can react this with alkyl halide. But we also want to make a cyclic ring, and let's see how we're going to do that. Okay, so we need to have a molecule that the halogen has to be attached to the same molecule 2 times, since it's going to form a ring. Now like this. decide which end will be the nucleophile and which end will be the electrophile. So this is going to be the nucleophile, these are going to be electrophile. So we need to add this part to this carbon. So then we need to have a two electronegative groups over here. Could be bromine, two dibromo compound. So you start with this one and then you add your base methoxide, so it will deprotonate here. So now you have this molecule with 1 2 3 4 5 carbons. 1 2 3 4 5 carbons. Both ends should have bromide on it or a leaving group, so it can attack one side first, leave bromide, and then when you add the next equivalent of the methoxide, grabs this hydrogen over here, make a negative charge, and then leave this bromide and form the cyclic compound. Okay. Another one. How would you make this molecule from this one? Now again, this is also a diester. Locate the new carbon-carbon bond that must be formed. Then choose the nucleophile and the electrophile. So this could be considered as the new bond that is being formed. So when you break this bond, we can have either nucleophile on this side and the electrophile here. Normally carbon is a carbonyl, carbon is a good electrophile. And this is the alpha carbon. We can have hydrogen removed from this alpha carbon and have that place as the nucleophile. Okay, so this same molecule you can make it in the bend form. So if you number them 1 2 3 4 5 6, 1 2 3 4. Okay, I did not start the numbering correctly. If you consider this 1 2 3 4 5 6, 1 2 3 4 5 6, it's the same molecule. Now we redrew it so we can see how the cycle is being formed. Okay, so when you add methoxide, nucleophile, number 2 carbon over here, number 2 carbon will deprotonate and can act as a nucleophile and forms the bond with this carbonyl carbon. Okay, and then you can lose the methoxy group. Yeah, so you want to make CH2 CH3. So yeah, so you want to add this part. So when you combine this one, this would make this part. From here you have CO, O, Me, and here you have O minus, O, CH3 after this, and then you lose this methoxy group, so you will get this part. That's how you get that part. That's how you get that one. Okay, so first you do the connection and then reform the carbonyl group, and then you lose a methoxy group, so you get this structure, which is this one. Okay, and then what you're gonna do is you're gonna react this with ethoxide. Why? Because we want to deprotonate this hydrogen over here. Once you deprotonate that one, So you're going to make a negative charge right there by deprotonating, and then you're going to react it with ethyl bromide and then the lead bromide. So then you can add this ethyl group into that alpha carbon. Excuse me. Okay. Because at the very end we want to have this group right there. Once you add that part, what you're going to do, now you're going to heat it with acidic water, and then when you heat it, this ester group over here will hydrolyze to carboxylic acid, and then the carbon dioxide will be lost. Basically that whole part is going to lose, and then you have your end product, this group over here. Okay. Okay, so that concludes our chapter about reactions at the alpha carbon. It's a wonderful chapter with a lot of information, and you guys learned a lot of ways that you can make new bonds. Very advanced chemistry. So proud of you. Okay, it looks like a lot, but it's actually not that much when you be able to learn the steps one at a time. Since you are hearing it for the first time, it looks like it's maybe it's hard to follow, but it's not really if you rewatch the video and try to understand what's happening. Okay, and then the best part is to do some homework problems so you can instill this information in your head and understand more. Okay, so I'll conclude the session here. I'll talk to you soon. Bye bye.